Hello, welcome to the 18th edition of the Nomadic Labs Research Seminar. Today it's a great pleasure to welcome Glen Mével. Glen is a PhD student at the INRIA Paris and the LMF Paris-Saclay lab. He's working under the supervision of François Potier and Jacques-Henri Jourdain. He develops Cosmo, a mechanized program logic tailored for Multicore OCaml. And today, Glen is going to show us how to put Cosmo to use by presenting us the formal specification of a concurrent queue under Multicore OCaml's weak memory model. Before we start, I want to encourage everybody to type in questions in the chat on the right during the talk, and Glen will answer them later during a Q&A session. Glen, thanks for joining us, and the floor is yours.
Thank you for the introduction, and thank you everyone for coming online. Maybe before I start, I should mention also that this work, my PhD thesis, is funded by indirectly by a donation from Nomadic Labs. So thank you, Nomadic Labs. And now for the talk. So the short title is specifying a concurrent queue in Multicore OCaml. So there are several things to say here. So we are interested in specification. So what do we mean by specification? We mean giving a formal description of what a program does in some mathematical setting, in some logical setting. We'll see the exact setting we'll use later, but I can already say that we will use separation logic. I will say more on that later. We'll study a concurrent. We'll study a concurrent data structure that is called a concurrent queue, and concurrency is the heart of this talk, of our subject, because we already know very well how to specify a sequential queue, but now the challenge is to specify a queue that supports concurrent accesses. And concurrency raises interesting questions that we'll see in this talk and we'll try to tackle in this talk. And the trouble starts even at the level of specification, not even going into the proofs. So that's why this talk is only about specification, because there is already plenty to say on this front. And the last part of the title is Multicore OCaml, because we're interested in, but we are in the OCaml community. We are interested in Multicore OCaml. So what is Multicore OCaml? Multicore OCaml, as the name suggests, is the multicore extension of OCaml for dealing with multicore programming, so parallelism and concurrency. As many of you probably know already, it is currently being merged in the main OCaml distribution. So it's actually the near future of OCaml. So we're actually interested in specifying Multicore OCaml programs. And there are interesting research challenges in Multicore OCaml, because Multicore OCaml relies on the weak memory model, which is a shared memory, which is a behavior of shared memory, which provides less guarantees than one will naturally expect. So it can have some non-intuitive behaviors, and that is for performance. We still must be able to reason about it. So the bottom line of this talk is that that reasoning about concurrency is hard. Weak memory is even harder. And in this talk, I will show how to write specifications for a data structure that supports concurrent accesses in this setting for Multicore OCaml. So let's start with something easier. Let's start with the sequential setting. By sequential, we mean no concurrency at all. So what is a queue? On an abstract level, we can say that a queue is a data structure which supports three main operations. The first one is called make. It takes no arguments and creates a fresh queue, a fresh empty queue. The second one is called enqueue. It takes a queue and the value, and it appends the value at the end of the queue. This last one is called dq. It takes a queue and returns the first element of the queue, if there is one. So how to specify this? Well, just like you're seeing on screen. So here we are using one whole triple per operation of the queue. So what is a whole triple? A whole triple is a precondition, an expression, and a postcondition. So the expression is a term of the programming language, but the precondition and postconditions are terms of a logic. So they are logical formulas for some logic we are using. The postcondition, so the meaning of this triple is that if the precondition holds and we run the program and the program terminates, then it returns value satisfies the postcondition. So here we have a binder for naming the return value. So the meaning of the triple for make is that if we have the postcondition true, in other words, if we don't have any precondition at all, we can run make, and if make ever returns, then it will return some value q, which satisfies isQ, the empty list. So what is isQ here? isQ is an abstract predicate. We don't know anything about it, except that it satisfies the three whole triples that we're seeing on screen. So this whole triple, this predicate, we call it a representation predicate because it represents a queue. So we understand it as saying that Q is a queue, and it stores the value which are listed in this list. So here we have so here, because we are in the postcondition of make returns an empty queue, so we have the empty list here. Now if we look at NQ assumes that we have a queue with some arbitrary list of values, and it appends its new value at the end of that list. And conversely, DQ, it assumes that we have a queue with some arbitrary list of values. It returns the first element of that list. It returns V, which is equal to V0. And now the queue has one less element. So a first thing that I have to mention here is that we are not, as I said, the postcondition only holds if the program ever terminates. So here in particular, we do not impose that the queue. We do not impose that the queue is non-empty before calling dq. So that means that we are allowed to call dq with an empty queue, and then dq should block forever and never return, because otherwise you will get a logical contradiction by getting that n is at least equal to 1, whereas you had n equals 0 here. Okay, something more interesting is that here you notice that we have used asterisks. So you may wonder what is this word symbol. So this symbol is actually you can understand it as a conjunction, and here we could have used the usual conjunction just as well. But this underlines that we're using separation logic. So what is separation logic? Very briefly, just to be clear, this talk is not about separation logic. So I will try to explain the bare minimum about this so that we can follow the talks. But I mean, having an in-depth understanding of separation logic is not a prerequisite to following this talk. I hope you'll tell me. So separation logic, the idea of separation logic is that each assertion of the logic not only is a fact that holds, but it also asserts the ownership of some part of the memory. So each assertion is really a resource that you own uniquely. In particular, assertions are non-duplicable because if you have an assertion, if you own something once, you cannot own it twice. It's contradictory to have two people owning the same part of the heap. So here, for example, is Q. This predicate not only says that Q is a region in memory which represents the queue with the given list of values, it also asserts the ownership of this region of memory. And in particular, we cannot duplicate it because otherwise we would have two owners for the same region of memory. So separation logic is a powerful tool for reasoning about resource consumption and resource usage in imperative programs, and I won't say much more about it. But that's the general intuition about separation logic. And yes, to wrap up a bit, we are using this asterisk is called the separating conjunction because it says that we have it replaces the usual conjunction in separation logic. Fine. So that was the easy part. Wrap up. So now let's move on to the hard part, and let's move on to concurrency. So let's say we allow for several threads to run concurrently. For now, we'll see we are entering the hard part, but the not too hard part. That is, we are still assuming sequential consistency. We'll say more on this later. But sequential consistency means that the program behaves as if it were in some interleaving of its threads. So the question that arises is whether does concurrency matter for the point of view of the specification? Is the specification still valid? So in fact, there are two questions. The first question is the specification we have shown for sequential for the non-concurrent case, is it still valid? And the second question is it correct? Is it usable? So the answer to the first question is that yes, it is still valid. The answer to the second question is that it is not actually usable because, as we have said, isQ is non-duplicable. It is exclusive. More than non-duplicable, it is exclusive. If we have, it is not possible to have two instances of the same isQ predicate. That will mean that we will have the ownership of the same region twice. So there can be only one thread at a time who owns the queue and is allowed to operate on the queue. So that in fact the queue cannot be shared at all. It's not shared among threads. Only one thread has access to it. So the spec doesn't allow for concurrent uses of the queue. So it's not useless. It's not pointless because it's already comforting that we can moving to concurrency does not break local usage of data structures. If we're using we can still use the queue in a purely local, thread local manner, and that won't break because we start being concurrent. We start being concurrent. So that's not useless, but that doesn't allow to use the queue concurrently. So now what to do to use the queue concurrently? So very first idea that we can have is to protect every access, every operation of the queue with a lock. So this is the idea, for example, that is at the heart of concurrent separation logic. So concurrent separation logic has been a development of separation logic for dealing with concurrency, as the name suggests. And it suggested to have a primitive notion of lock that you could protect operations with. And lock are runtime operations, which satisfy locks are a runtime component which satisfies two operations. The first one is acquire. You can acquire a lock, and you can release a lock. from a logical point of view, also acquire, you have acquire and release pairs. They delimit critical sections, and you put all of the accesses to the queue, all operations of the queue inside critical sections. And now, from a logical point of view, you can give a logical specification to a lock by saying that the lock guards an assertion I, some assertion I, and that acquire, you can acquire the lock without any condition, and it gives you, as a result, the assertion I. And conversely, you can release the lock if you have I, and it gives you nothing. In other words, you have to return I when releasing. So what does that mean is that what does that mean is that the lock itself guards, the lock itself owns the assertion I. Remember that an assertion in separation logic is a resource. It's for example, a part of memory or a file or anything really. So the lock, when it is unlocked, it owns I. But you can take ownership of I temporarily by acquiring the lock, in which case you are the only one owning I. And at some point, you have to return I to the lock by releasing the lock and letting others acquiring it. So I will rewrite this a bit by using the frame rule. So instead of having true here as a precondition to acquire, we can have a P, an arbitrary P, which will not be touched by acquire. So now as a pass condition, we have P star I, well, because we have still P untouched and we got I. And conversely, for release, we can get, if we have I star Q and we release the lock, then we get Q. The reason I just did this small rewriting is that we can now give a specification to this combined program. If we have some program that satisfies P star I, that satisfies the whole triple with precondition P star I on I star Q, then we can protect it, put it inside a critical section, and we will get the whole triple whose precondition is P and whose postcondition is Q. So if we have E which satisfies this whole triple, P star I star Q, then we get the whole triple, the expected whole triple. Right. So how do we use this for our Q is that we just put the ownership of the Q in I. We have to quantify existentially the state of the queue. So the n on so this list here, it is quantified existentially here. So now everyone can so everyone can acquire temporarily the ownership of the queue by acquiring the lock. But there is a last difficulty is that now the state of the queue is quantified existentially inside I. So outside of I, we don't know anything about it, so we can't say anything useful about it. So if we want to say anything useful about it, we have to say it inside of I. So we have to add some some assertions that depends on what we want to do with the queue. So we add some assertion about the public state of the queue. Okay, so that's fine. We now have a general recipe for taking any sequential data structure and turning it into a concurrent data structure for easily. And that always works. But there is a downside. What is the downside? It is that it requires changing the program a bit, and it requires inserting runtime operations in the program. The lock is a runtime operation. So that is costly. And that is even more costly because you create a lot of contention. And in fact, you can do better than that. You can design data structures that support such that the set of operations allowed are consistent with each other and already support concurrency. So that has been a research field of intense research. So there are many algorithms and data structures that are already concurrent without the need for protecting them with a lock on top of them. So you can have better performance with that. And then you don't need a lock anymore. But now the question is how to specify these concurrent data structures without using a lock. And for that, an idea that has been developed in several successors to the first separation logic is to use an invariant. So an invariant is similar to a lock. It's in that it is an assertion that holds at all times. It satisfies a similar rule, but by contrast with a lock, it has no runtime component. So it is a purely logical thing. It is a feature, a built-in feature of our separation logic. And what I should mention here, yes, I should mention that here on my slide I've put that it is a feature of Iris. So I'm mentioning Iris here because that is a separate. So Iris is a framework for separation logic. It's what we will use from now on. So Iris relies heavily on invariants, which are one of its core features, but it's not the first separation logic to feature invariants. Hey, okay. So I was saying that in a separation logic such as Iris, we have a logical notion of invariance. An invariant is an assertion that holds at all times in all threads, and it supports the exact same rule for the same rule as for locks that we have written in the previous slide. Only we do not need to insert any runtime operations. So for proving the OPPEQ, if I is an invariant, it is enough to prove the OPP star I E I star Q. We call this, in other words, we are allowed to open the invariant locally around E. So we can get I as a precondition to E if we return I back just after he has returned. Yes, just so for the remaining of this talk, the Iris notation for the fact that I is an invariant is this box I. Right. So just before, just as with locks, we can now store the ownership of the queue in I, and everyone can get the ownership by opening I. And there is the same remark that we should do something about the state of the queue inside I. But there is a condition that I've not mentioned before, that I must mention now, is that this rule is only valid if E is atomic. And atomic here, the meaning of atomic here is very syntactical. It means that E reduces to a value in at most one step. So it's very restrictive. And the reason why we have this restriction is that remember, we are in a concurrent separation logic. I has to hold at all times. If E weren't atomic, then another thread might be interleaved with E and might be allowed to observe a state in which E might have temporarily broken I. And this must not happen. So we add this restriction that E be atomic. Right. And this restriction is the problem. It's an actual problem because it's a very syntactical criterion, and most probably we would like to be able to open the starting point of this talk is that we wanted to open an invariant around the operations of our queue and Q and the queue, because we want to put is Q, the ownership of the queue, inside an invariant. But we can't because we don't know whether NQ or DQ are atomic. That's an implementation detail, and in fact, they most probably aren't atomic. Yeah, they most probably take several steps to compute. So we cannot use this rule. So what to do now? NQ and DQ are not atomic. However, it is a reasonable assumption from the user perspective that they behave as if they were atomic. So and as a user, we can expect, we may expect that they behave as if they were atomic. A term for that is we call them linearizable operations. And we would like to be able to open invariants around such operations. We would like to open invariants around such an operation as if it were atomic. So what do we do? The solution is simple. In fact, the solution looks simple at least. So we can't do what we want with the usual four triples. Solution: define another kind of four triples. So we define what we call logically atomic four triples. We denote them by these angle brackets instead of the usual curly brackets, and we define them such that we are able to open an invariant around them as we want. We define such that we have the rule we want, in fact. What is the meaning of this? The meaning of this Hort triple, of this logically atomic triple, is that first we have the usual Hort triple, PEQ with usual curly braces. So we have the usual interpretation of the triple. Plus, we say that E behaves atomically in some sense. To be more precise, we say that E is linearizable, by which we mean, even more precisely, that E has a linearization point which satisfies the usual Hort triple P with precondition P and postcondition Q. So what does that say? So what we call a linearization point here is a point inside of the operation such that everything happens. It's as if everything happened during that linearization point. So E can span many steps of computation, but it's as if everything happened during that single step of computation, which we call the linearization point. And because that linearization point, at that linearization point, we say that we have the usual Hort triple with precondition P and postcondition Q. And because the linearization point is a single step for computation, it is atomic. Because it is atomic, we can open an invariant around it. So we have the usual. So we have the rule for opening an invariant around a logically atomic Hort triple. So something that I should insist on is that if I have the logically atomic triple P, E, Q, it doesn't mean that we have P from the beginning and get Q at the end of E. It means that we have P just before the linearization point, and we get Q just after the linearization point inside E. So in particular, P and Q can talk about the state of the queue, which will only be known, for example, if we come back to our example with the queue. So P and Q can talk about some state, which is only known at the linearization point. We don't know it ahead of time when starting to execute E. So we have to bind it at the linearization point. And for that, we add a binder to the Hoare triple. That's the purpose of the X binder here. So here, X is bound in P and in Q. So that's a technical detail. And I think that's all. Yes, and okay, last, sanity check, safety. As I said, if we have a Hoare triple, the logically atomic Hoare triple entails the corresponding Hoare triple, usual Hoare triple. So that's not an insane notion. It's a stronger notion than the usual Hoare triple. And now I think we have all the ingredients for writing concurrent specifications for the queue. So let's do that. So let's start by writing the specification of make. So for make, we don't need to use a logically atomic Hoare triple because there's nothing to share yet. We are just creating the queue. It does not exist yet. So we still have no precondition, and we get the predicates representing the queue, but we have changed the representation predicate a bit here. That's mostly for technical reasons. I won't explain why we did this, but I need to explain what are those two predicates now. So now instead of a single predicate isQ, we have two predicates QInv and isQ. QInv of Q and gamma represents the knowledge that Q is a Q in some state, but it doesn't assert the ownership of the Q. And it doesn't say what the state is. So this QInv, as the name suggests, it is an invariant, so it's always true, it's duplicable, and it's freely, so we can freely share it around among threads already. However, isQ is the part that is exclusive. It represents the exclusive ownership of the queue, and it says what the state of the queue is. So here we are using gamma, the Greek letter gamma, which is a ghost name for the state of the queue. So ghost name is another feature of Iris. So it's a name that we give to a piece of ghost state. I won't enter into more detail here, but what we must understand here is that QInv binds the ghost name gamma to the physical location Q, so that isQ only talks about the ghost name gamma. So gamma is a piece of ghost state that stores the physical, the idealized state of the Q. Idealized in that it's a Coq list of values. So as I said, QInv is duplicable, so we can share it among threads freely or free. isQ, however, is exclusive. And if we want to share the ownership, it represents the ownership of the queue. And if we want to share the ownership of the queue among several threads, we need to put it inside an invariant. Fine. So now let's write the specification of NQ and DQ. So here are the specification of NQ and DQ. That's a bit That's a bit impressive, maybe, but in fact, with everything we said before, we see that it's not that complicated. It's the same it's exact same specification as in the sequential setting, except with the difference that we have replaced the usual Hoare tripole with logically atomic Hoare tripoles. We have explicit quantification here. And we are using the twofold predicate, representation predicate. So we have is Q, the exclusive ownership of the Q. We only get it at the linearization point of NQ, of the Q. But the shared invariant of the Q it holds at all times. So it is a precondition of the. It is a general precondition of the logically atomic Hoare triples. Fine, so with all that, we have a working specification for a concurrent queue in a sequentially consistent setting. And now for the really hard, let's move on to the next level. So I promise that we will say a few words about wake memory. So what is wake memory? So as I said before, sequential consistency is when the behavior of a program is some interleaving of the execution of all of its threads. So if we consider this a very simple example program, maybe you have seen it already, you can find out that the possible outcomes from this program, if the outcome is A, B, are 0, 1, 1, 0. So 0 if you execute it this way, 1, 0 if you execute that, if you execute the program that way, or 0, 1, or 1, 1 if you execute the program that way, or in the opposite direction too. But you can prove mathematically, it's a very simple proof that you cannot get 0, 0. It's impossible. That is, if you assume sequential consistency. But if you run this program with Multicore OCaml, if you run it 1,000,000 times, for example, in the loop, you will find that you get 0, 0 sometimes. And that's very unexpected. And the reason for that is that sequential consistency is not the memory model of Multicore OCaml. It's not the memory model of usual compilers nor processors. So the compiler, is it a bug in the compiler? No, it's not a bug in the processor either. It's done on purpose. Both compilers and processors perform some optimizations that break sequential consistency. And that's not a bug. That's on knowing that they are knowingly doing that. So we have to cope with that. So they still give some guarantees about the behavior of the memory, but they give less guarantees than sequential consistency. And how to describe these guarantees? Well, we have to give a model of the memory. And everything that is not sequentially consistent, we call it a wake memory model. So the essence of wake memory model is that each thread has its own view of the state of the shared memory. So for example, one thread might think that X has value 5, while another thread at the same time might think that X has value 3. And our challenge has been, in the last decade or so, a challenge is in language design and program verification has been in describing formally such wake memory models. And this has led to several memory models being described, the most famous one being C11. More recently, there has been a description of the memory model of Multicore OCaml. there are several different ways of describing a memory model, but what we're interested in here is that these memory models can be given an operational semantics based on the notion of views. So an operational semantics means that we still have small step semantics. We say at each step of execution how there is an object that represents the global state, the global memory, and we say that each the execution of a program is an interleaving of the execution of all of its threads. And at each step, we say how the global memory is updated. But it's not sequential consistency, because the main memory, the global memory, is an object much more complicated than just a simple mapping from locations to values. And threads are something more complicated than just an expression. They also have some local states that, on this local state, determine how the threads interact with memory, how they see memory. So this local state, we call it the view of the thread. And that's interesting for us, having an operational semantics, because we know how to build a program logic from this operational semantics, and that's what we have done for Multicore OCaml. The resulting program logic is called Cosmo. So what is Cosmo? Cosmo is a program logic for Multicore OCaml, for the weak memory model of Multicore OCaml. It is built on top of Iris. Iris being a general framework for building program logics. So from Iris, we benefit. We benefit from all of its features. So we get separation logic, we get ghost state, we get invariance. More on that later. We also get the fact that it is mechanized in Koch with a mechanized proof of soundness. So that's nice. We get very powerful features. And the key characteristic of Cosmo is that assertions are subjective. By subjective, we mean that the validity of an assertion depends on the thread's current view of memory, a priori. So, for example, if we look at the typical separation logic assertion, x points to 42. X points to 42. Intuitively, it means that there is a memory location x, which stores the value 42, and we own that location, but that's another issue. But here it means something more. It means that the memory location x is in some state such that, to the best of our knowledge, the value of x is 42. To the best of our knowledge, that means according to our current local view of the memory. So this assertion is typically subjective. The issue, so the issue with subjectivity is that invariants, they have to hold for all threads equally, which means that they cannot depend on one thread. Their validity cannot depend on what a thread has observed. It cannot depend on the current view of the thread. So invariants, in fact, in Cosmo are restricted to objective assertions, by which we mean that an objective assertion being one that doesn't actually depend on the thread's current view of memory. So if we go back to our queue, we want to share the ownership of the queue inside an invariant. So to put is queue inside an invariant, it has to be objective. So we add to the specification, in addition to the 3 whole triples, we add that is queue is objective. So now, with all that said, we can ask the same question as before. Is the spec still valid? The spec that we have written before, is it still valid? And is it usable? The answer is yes, it is still valid. The second answer is it is usable in some limited cases, but there's something missing, which is very important, which is synchronization. When transferring a complex value, a complex value being a complex value is something that can span several blocks in memory. So it can there have been several write events to that value. And when a dequeuer gets a value from the queue, it must, in order to manipulate this value properly, it must have observed all the write events which have happened on that value, to that value. So for that to happen, there must be a synchronization from the enqueuer to the dequeuer, because that's the enqueuer who has all the knowledge a priori of the write events to the complex value. So we translate this in our logic by the fact that the enqueuer acquires the view of the dequeuer. The dequeuer acquires the view of the enqueuer. So what is a view in Cosmo? What are views in Cosmo? So a view it's an abstract notion, but it is equipped with a notion of order, of inclusion. Larger views correspond to more knowledge, or more recent knowledge, or better knowledge, more write events known. And how to manipulate them in Cosmo? We have a separation logic, a special primitive separation logic assertion in Cosmo, which is not denoted upper OV, which means that the current view, the ambient view, the view of the current thread, contains at least the view V. So now, if we come back to the queue, we want to assert that, as I said, we want to assert that not only from an enqueuer to a dequeuer, not only we transfer value, but we also at the same time transfer a view. So how do we specify that? We just add the view, we just add the view corresponding to each value in the representation predicate. So now the representation predicate, the public state of the queue, instead of just being a list of values, it is a list. It's a list of pairs, value views, and we specify and we added to the specification of enqueue that the enqueuer pushes its view inside the queue. So we say so the upper OV here means that in precondition means that this will be any write event that is known to the enqueuer can be put in the queue. So that's reminds you. It may remind you of release acquire in C11. And conversely, when dequeuing, the dequeuer acquires it as a post in its post condition. It acquires it in its own view every write event that was known to the enqueuer. So that's that looks very similar to the release acquire pattern in C11, and that's not by coincidence. That's really the same thing, and that's how we specify it in Cosmo. Yes, I'll skip that. Yes. Okay. So that's finally how we write the specification in Cosmo for concurrent queue. I think we said it all. And now we come to the conclusion. So the bottom line is that concurrency is tricky. weak memory concurrency is even more tricky, but we can cope with them thanks to several concepts, which are logical atomicity, plus a logic of views, which is embodied by Cosmo, and that the combination of both enables, there are powerful tools, and that the combination of the two enables to write usable and actually usable and expressive specifications for concurrent data structures in concurrent setting with weak memory. I haven't said, I've only talked about specification, but I haven't said anything about proofs. But of course, we can also write proofs with this logic, and it works. So we have a proof for a concurrent queue library, which satisfies this specification that I just shown. So thank you for your attention, and if you have any question, I will be happy to take them now.
Okay, thank you, Glen, for the presentation. We still have a few minutes for a few questions, so I will start right away with a question from Jan. He was asking on the slide at the beginning on slide 1, what is the type of queue? If queue is a queue, if queue means queue, then it's weird to have is queue queue. I guess you mean a pointer.
Yes. So I share my screen again. Up. So queue is a pointer. It's a memory location.
Mm-hmm. Okay, but then, and I mean, this is his follow-up. It's on the slide 6. You have changed the type of queue, right? Because then you are actually using the ghosts.
Yes. So here.
Yes.
Yes. So we have changed the predicate isQ a bit. So the type of isQ has changed. Yes. So now it's no more memory location. Here it's a ghost name that we put. Indeed.
Okay. Yeah, there was a second question from Jan. He was asking, I guess it's slide 4 or something, about the definition of what actually atomic means. So what it actually means to do atomic execution. Okay, maybe I said it. I think I said it. So maybe the question was before I saw it, but I can say it again. So E being atomic means that E is an expression of it's a term of the programming language. Mm-hmm. We have small step semantics for the language. And E being atomic means that E reduces to a value in 0 or 1 step. Okay. So we have another 2 questions, so maybe we can take them quickly. So Jan again asks, he's not sure he understands how to exploit the acquires view and to reason about the queue. So how do we deduce that the property is objective from the example? I think he was speaking about. So sorry, I didn't get the question. Is it about this slide? I think. Yes. How to exploit that acquire view? I'm thinking how the client of the logic uses the fact that. Right, it's something that I haven't written on slide. I'm sorry for that. Okay, so if we look at the rules of interest are the 3 in figure 4. Mm-hmm. So I've been very quick on this because I was running out of time. But the rule that answers Jan's question is that one. So maybe before I should say a few words about this one. Okay, no, sorry, that's not useful. So we have 2. So in fact, we have 2 operations about. Sorry, we have 2 primitive constructions in the logic to talk which talk about view. We have the upper V that I showed in the talk, and I have the P at V operation. The P at V connective,
What P at V means is that P holds. So P is an assertion. P is a subjective assertion, and V is a view. And P at V is an objective assertion, which means that if the current view of the thread was at least V, contained V, then P would hold.
Mm-hmm.
Is that clear? So in fact it's a way of turning a subjective assertion P into an objective assertion. You simply make it explicit what is the view, which is enough to make P hold. Mm-hmm. So and what's interesting with these two operations is that you have this rule for any subjective assertion P. You can split it into a subjective assertion upper V and an objective assertion P at V for some view that is in fact that should be in fact the current view. Mm-hmm. So that is interesting because this is purely subjective, but you can transfer it as we have just seen through the queue. You can transfer such assertions via the queue, and this is objective, so you can share something like that. You can share it in an invariant directly because it's objective. And it's an equivalence. It's an equivalence. So if you have P, you can split it into these two parts, and if you have these two parts, you can pack them and get P back. So,
and I take that it's the burden of the person doing the proof to come up with the V. So I have a P, and then I need to produce the view.
So as the enqueuer, what you will do is when you enqueue, you use this tool from the left to the right. You get some in your proof context, you get some view V. You know nothing about it, but except that you have these two predicates. Mm-hmm. It's not a problem that you know nothing else about it. You push this view inside the queue, and probably you will provide this. You will transfer it via an invariant. Mm-hmm. And as the dequeuer, you will get this when dequeuing. You will acquire this. You will get this. You will retrieve this from the invariant, and you can wrap it up and get P back.
Okay. So we have one last question from Jean-Marie Mével. He's asking, how do you use the logically these specs to prove a concurrent program?
Okay, that's a good question. I haven't shown how we define logically atomic or triples. There is a definition from them. Okay, in fact, it's in this very. Do it. It's a bit complicated. It's a bit technical, but the intuition is that. So this is a simplified definition. It's not even the full definition. It's a simplified definition of logically atomic or triples. Essentially, what we say is that we define a state transition system, more or less. So we say that if we have P, yes, sorry. Okay, it's a bit indirect because it's quantified over all past condition. So sorry. What? So this is a precondition. So intuitive. At a high level, what we say is that if we have P after possibly some score state update, if we have P and we have that phi. That we can update sorry. Okay. Maybe it's too technical to explain in a short time, but mostly we say that we describe we describe the transitions that are possible for So the OR triple says that we can transition from P to Q atomically at some point, and it's what we say here essentially.
Okay.
And the actual definition is more complicated because we also want to allow aborting. It's something that's not useful in our case, so it's not shown here. But the idea is that sometimes we want to get P, or to get what the resource that is in P. I mean, I'm not speaking clearly. So E is an expression which can perform many steps of computation, and normally we will only be able to get P at the linearization point, at one specific step of the execution, which is the linearization point. At which point we should provide the path condition immediately, and then we have lost P. But sometimes we want to access P earlier. That's okay if you just return P back. You want to access P before the linearization point, and then you need to have a more complicated definition that says that you can access P, but you have to return P back immediately.
Okay, I think that we are being cut out. So,
okay.
So thank you everybody for joining us. I think we can all thank Glen for the presentation, and we look forward to reading the rest of the details in the upcoming paper. And again, thank you all for joining us. This is our last session of the season of the research seminars, and we will be back in September with more presentations. So thank you and goodbye.